Alright, so today there's actually quite a bit of content on sorting and stuff. I'm going to try to breeze through a lot of the talking points, kind of explain them, and then we'll go into and do some of the exercises. I want you to see this stuff, but I don't think that we should spend the entire time on it if we don't have to, so you guys can still work on your projects. But it is important stuff to see. So we're going to talk about it. Also, somehow on my way to class, I split my lip, and so if I dab on my lip that continues to reopen, that's why. I don't know what I did. It was like chewing on my lip or something, and then bam, it was horrible, you know? It's a terrible time. So, yeah. I don't know how that happened. But anyway. Alright, so Monday we talked about basic algorithms, pretty much just kind of searching through an array, and one way we could potentially make it more efficient. So by using like a binary search instead of a linear search, right? There's ways that you can devise clever algorithms for breaking down what you're searching through into subsections, and you can try to search through subsections instead of the entire thing and eventually whittle your way down to where you want to get. The whole point being that the study of algorithms and data structures is to make our processing time more efficient, right? Better use of our processing time. Every time you add some data element or data point to a calculation, it's going to take longer. There's going to be more machine instructions involved with calculating whatever result you're trying to get, and you lead to inefficiencies if you're careless about those kinds of things. Do they affect us, you know, as general web developers most of the time? No, they really don't, because the problems that require this kind of solving have pretty much been solved, and we're dealing with way high-level stuff. But knowing it's not a bad idea, because every now and then you're going to run into this kind of stuff in work, or you may have some rendering thing that's slow, whatever. So today we're going to talk about sorting, which is really kind of like a big part of the introduction to algorithms, because they're sort of the easiest algorithms to understand in terms of what they're doing. But there's some very complicated algorithms for actually accomplishing a sort. So they're a good kind of gentle introduction in that regard. So imagine we have all these numbers, and we wanted to sort them by hand. What would be the kind of intuitive approach to sorting them by hand? Anyone?
For loops to iterate over it?
No. By hand. You have these on blocks.
Oh,
I don't care about your loops.
2 digits to the one side, 3 digits to the other side.
So you'd start breaking them into digits, and
then by digits. I'll just put them one underneath.
Visually,
one underneath another one. And
okay.
First have to be 1, 2, 3, 4, 5.
Okay, that's a good strategy. Try to like visually kind of determine based off of what you can see. That's a good one, and there are sorts that are kind of like that. Another kind of simple approach is scan through the list, find the smallest one, put it first, right? Move it first. Scan through the list, find another one, move it second, and just kind of replace them in that way, right? That's a pretty intuitive, simple approach that people kind of go to first when sorting, because it's really easy to understand. We know exactly how that works, right? We find the smallest one, we move it first. Okay, well, if we do that with everything, we find the next smallest, eventually we'll have them in order of smallest to biggest, right? So there are more complicated ways that are more sophisticated that may end up in better results in terms of overall time, but the point is, how we intuitively would sort something is pretty simple, right? Generally speaking. But it would take a really long time. I mean, this could take you, 30 seconds, 45 seconds if they were in block form, right? To scan through all of them and do it. It takes a really long time. And that sucks. Because there's probably more efficient ways to do it. Maybe not for us as humans, but, for a machine, there certainly are. However, that basic intuitive approach to sorting is a very common sort method called selection sort, right? So the whole point of selection sort is you'll take a list of numbers, you'll scan through the list, find the smallest one. When you find one that you think is the smallest, you'll continue scanning through the list to see if there's one that's smaller. And if you don't find one that is the smallest, you'll put it first in the array, right? So you have an array of numbers. You look for everything. We imagine everything's greater than 0, okay? So the smallest possible number there could be 1. You find the smallest one. As soon as you found it, you've gone through the entire array. You put it first in the array, right? Maybe you swap it with whatever's currently first in the array because you know it's smaller. Or you put it in a new array. It doesn't really matter. Point is, you know that's the smallest item. You go through it again. You'll have something that's slightly bigger than that, but smaller than everything else, right? So you'll find that one. It'll be second, right? So on and so forth. So selection sort. It's a pretty simple sort to implement because it's a pretty simple sort to think about, right? We're literally finding the smallest and moving them first and just continuing to do that. So what you're going to do is implement selection sort. So activity number 3, there are some examples. Granted, I gave you guys all the solutions for this week. They're already in GitLab, so if you download this GitLab stuff, you have the solution. Don't look at it. Come on, do yourself a favor. At least try. Activity number 3, selection sort. I want you to give it a shot. I'm going to select out the instructions, and we're going to start playing with some algorithms here today. You can just create a new node file if you want, or use the example that they have, the starter example. People still working? Okay, I'm gonna take that as a no then. All right. So why don't we look at this selection sort? So they gave us some stuff here to help us get started to generate the array. They give us a swap function, which just takes it from one array and puts it in another array. So what do we got to do with a selection sort? How does this actually work? Well, the first thing we need to do is, I mean, you guys all got the solution. We can look at the solution together. Just paste the code. Okay. So, setup stuff. We want to find the length of the array, set a minimum value that we're going to hold in a variable, right? And then here we can start going through the array. We'll start at the first element, item 0. We'll immediately assume that that item is the next to minimum element. It's the reasonable thing to do. And then we're going to go backwards, or then we're going to go through the array again, starting from the next element in the array. Okay, so if we're at 0, we're going to start at 1, and we're going to move forward from 1 to see if there's anything smaller. And if there is, you can go ahead and determine, okay, well, this is what the actual minimum is going to be, which you can see here. Okay, so we have our current minimum is going to be this index, right? If the index we're looking at is less than that, well, then that's the new minimum index. Then eventually, if you happen to have an index that isn't the current I that you're on, you can swap those two items in the array, right? So we'll take the first index is going to be I, and the minimum index is the second index. And we take the array, we take the value out of the first index, we put the value in the second index and put it back in the first index, and then we take that original value and put it in the second index, and we've got a nice swap. If you go through the entire array doing that, eventually you'll get to the end, after going through everything multiple times, where you'll have this sorted array, right? So we can just run it. Not even close. So at the end, we have a sorted array. What'd you say? Well, they're randomly generated. So, they are. They'll be different every time. The important point is they're sorted. They should be sorted at the end, right? So, visually, we can actually see what this looks like. There's this Visualgo, I don't know however you want to pronounce it, website that Firefox, for everything good it does, you can't just drag a tab super easily. It's a pain in the ass. Oh, anyway. So the selection sort here, we can see how it would work. We can actually visualize this whole process, right? Okay, well that one seems to be the smallest, so we're going to swap them. What's next? 14 seems, 13 smaller. We'll swap that with what's next. 14 smaller, and then we can swap the last two. We have a sorted array, right? So visually, that's what's happening with the selection sort. So again, it's a pretty simple sort. Questions on this selection sort, how it works, kind of what we're getting into. So one of the big problems with selection sort is while it's simple, it grows what's called quadratically. So for every item we have in this array, we have to loop through the array an entire time again, right? So we have 2 items in the array. We have to loop through that array effectively twice for each item. So we go through the first one. 2 is a small number, so it's not a big deal. We have to loop through the array again. We have to see if the second number matches. And this one's kind of simple, right? Because you go through it once, you'll either flip them or you won't. But even if you have 5 items, you go through the first one, and then you have to look at the next 4. And then you go to the second one, and then you have to look at the next 3. Go to the third one, you have to look at the next 2. Anyway, what happens is, the way to calculate how long it's going to take is basically take the items in your array and times it by itself, right? So for 3 items in an array, you've got potentially 9 calculations that you have to do, right? For 4 items, you have 16. For 5 items, you have 25. And you can see as the number gets bigger, so does that difference, right? So for every number, it gets you know, a whole power power of 2 longer to execute this this sort function. So it's not that efficient. You know, that's pretty bad in terms of time complexity, as it's called in algorithms. Because if we had a huge array, some massive hundreds of millions of elements, it's like never going to finish, probably. And it's going to take forever. Doesn't matter how fast your machine is, eventually just the number of calculations. Yeah?
So, is there like a scenario where you, I guess, where you use this in a real life scenario? Like you were coding something where you want to use this?
Yeah, that's a great question. Yeah, actually. So, JavaScript has a sort function, which we've used a couple of times. And it actually uses a selection sort. It's either selection or insertion, I can't remember. But it uses one of these very simple sorts with items, arrays of less than 10 items. So for simple sorts with not a lot of items, the next one we're going to look at, insertion sort, is an important one you can still use. It's not any faster necessarily than this one, but it's still really simple to implement. And so when you have a small array, you might as well just use the simplest implementation. So if you can guarantee you have a small array, using a simple sort is fine. Outside of that, we get to far more complicated but far more effective sorts, which we'll talk about later. So, questions on the selection sort. So what's a simple way that we could make the selection sort slightly more effective? Worst case scenario won't be any better, but generally speaking, it's more effective. Well, there's a sort called the insertion sort that we'll look at. I don't know if I can ever open it. That's very similar. It's still quadratic time complexity, which means it's still gonna, worst case scenario, it's gonna take as long as the number of elements in the array times the number of elements in the array, right? So it's not worst case any better than the selection sort. However, it turns out most of the time that's not what happens. It's not the worst case scenario, so it actually ends up being better. So it's still a very simple sort, but it's slightly better in real world scenarios than the last one we did. So we'll see how this one works. So swap the first two. And then what it's actually going to do is go backwards from when it finds the smallest number to see if the numbers before it are smaller. So where the last one would take the first one, it would go all the way through, it would find the smallest, move it first, go all the way through again, find the smallest, move it second, all the way through again. This one actually tries to find the smallest or find a smaller one and just start swapping them, as opposed to going through the entire array. So what happens in reality is, as this array gets really large, odds are you're not going to have the biggest in the beginning of the array and the smallest at the end of the array, which would be the worst case scenario, right? The totally reversed order to everything. It's going to find things in nice places, so it'll be like, okay, I got halfway through the array, I found something smaller, I can just start swapping these things, and you kind of work your way partially through the array on each iteration as opposed to completely through the array. So while the worst case, again, is the same as the selection sort, what actually happens in real life is it's more efficient. And this is still a very simple sort to try and implement. It's called the insertion sort, right? So now what we're going to do is look at activity number 4, use the pseudocode that the instructions have for you, and we're going to try to implement the insertion sort instead. I'll slack out these instructions.
Just like a wild stuff that's supported, or is it just not feasible or possible?
Is that what we're trying to do?
No, I'm just curious. Because like in the last, not this film, the last one, that's how I was thinking about it. Wild, like the first.
The for loop just comes with the built-in iteration and stuff, so it's more convenient. But I don't think there's like a difference in what it's assembled into, so it's not like one's more performant or anything. Are people still working on this one? No? Nor says no. Do we want to go over it now? Yeah. Okay. Alright. So the insertion sort. It's, like I said, it's worst case scenarios, not more efficient. Actually, an interesting thing to look at is what Chris slapped out on Monday. So we can see here that selection sort and insertion sort, you can actually see their times, worst, average, and best case scenario. So generally when we're doing algorithms, we think of their worst case scenario. That's how we compare them, right? So these two are functionally equivalent in the worst case and average case. But insertion sort has a best case scenario, which is this omega of n, right? Instead of big O, it's big omega of n. That's linear time. So best case scenario, we get linear time. So that means the reality is we get some weird mix between linear and quadratic time, and that's cool, which means it ends up being a little bit better, right? But it's just very marginally better. However, it's marginally better without being really any more difficult to implement, so in that case you might as well go with the marginally better version, right? Okay, so what do we do this time? We have our items. We have an I and a J we're going to use because we're going to be moving through the array kind of weird in tandem. So we're going to start at the beginning. That's going to be our first value. And we're going to be starting from, we're going to go backwards from the first element we're at down, back to the beginning of the array. Okay? So in this case, the first iteration is just going to skip, because we're starting at I minus 1, which is going to be -1, and we only go while j is greater than -1. And while we still have this scenario where what we're taking and what we're comparing it to, the item that we're comparing is smaller than what's on the right-hand side. So this one's kind of a little bit harder to explain. Basically, we have the item here at I. Say this is 5. And if the item on the right-hand side, which is going to be our I, right here, this value, if it ends up being greater than the item in J, which is the one that's right before it, we're done, right? Because we know the item in J is already sorted appropriately compared to I. If it's not, if it's the case that the current value at I is greater than, or is less than whatever's in J, so we're at element 4, or 5, and we have element 4, right? So it turns out 5 is less than 4, we're going to go ahead and swap them, and we're going to continue working down the chain. So, okay, great. We swapped them, so now we're in element 4. If 3 happens to be greater than, we'll swap then, and it turns out 2 is less than what we've been swapping, we're done. And so that's how this one ends up being a little bit more effective is because it doesn't necessarily need to go through the entire array the second time. The selection sort goes from bottom to top each time it goes through the array. This one goes from wherever we are down, and if we've already sorted the things before it appropriately, we don't have to do any more work. At that point, we just do potentially one swap or nothing. So we can actually, we'll debug through this code because it'll make it a little bit easier for us to see what exactly is going on. Actually, I can just use the launcher. Okay, so we have a bunch of items. We have 40 items. What's going to happen is we'll take the first item, which is 13, and we're going to set j equal to I minus 1, which is going to be -1. So we're just actually going to end up skipping the first iteration. So this is where I is 0, right? And so our first item in the array is going to be itself. So the first iteration doesn't do a whole lot. You could probably actually skip it, but you're not going to gain a whole lot by doing that. So second iteration, we're at I equals 1, right? So the value is 37. What we're going to do is we're going to set j equal to 0, so j is I minus 1. Is j greater than -1? It is, because it's 0. And is the item at j, which is 1 to 37, greater than the value, or is the item at 0, 13, greater than j? No. So our condition is done, right? So we skip again, and nothing is swapped in this scenario. So the third item is 33. Okay, so here's an interesting one. So now we're at index 2. If we look through the items, we have index 2 right here is 33. Index 1 is 37. Index 0 is 13. So these two got to be swapped, right? So in a selection sort scenario, we would get, we would have a slightly different layout already, but when we got to this one, say we got to index 2, we'd have to go all the way through this entire array to find out where it needs to belong, right? But in this case, we can set j equal to 1. We can start there. We can say, hey, is the item at 1 greater than our current value? The answer is yes. Well, why don't we actually swap those two? Okay. So now we have 37 is in our current index, and j is our last index. So our value, our 33, doesn't exist in the array anymore because we've moved what was in index 1 up an index to index 2. But the condition no longer holds because 13 is smaller than 33, so now we'll put 13 wherever j was, right? So it's going to be index 1. And then our array now has swapped 33 and 37. So what we've got is, instead of going all the way back up the entire array on that second index, we have been able to just swap one pair and when we're done. Well, this one, index 3, is going to be even more interesting because it's got to go back 2. It's got to go to index 1, right? So it's going to be moving 2 places forward in the array. Or backwards, however you view it, I guess. So we set j to 2. We're going to say, hey, is the array at index 2 greater than the array at index 3? Yes, 37 is the array at index 2, and 14 is what we got now. Okay, so we're going to swap them. So if we look at our array now, we have 37 again in index 3. Hey, is the item in index 1, after it decrements, is the item in index 1 greater than 14, which is the one we're trying to compare? Yes, it is, because it's 33. We can swap those as well. So now we have 33 in index 1 and 2, and 37 in index 3. We'll decrement one more time, and we see that j is 0. So now if we look at our array, 14 is where it needs to be, right? So if I go ahead and jump ahead, now we've got a sorted array. So this one is a little bit more complicated, but only marginally so, because we're basically going backwards through the array and just trying to swap as we go, as opposed to going all the way through and making sure we have the smallest one and then swap. Yeah, Matt?
So does it matter if you call it j?
No, you call it whatever you want. It's just an iterator, right?
Can you do that with a while loop?
Sure, but then you have to manually do the math to, like, decrement and stuff like that.
Yeah, you just do j minus 1.
Yeah, but I mean, the for loop does it for you. You can do whatever one makes you feel better. It doesn't really matter.
More code than I do.
This is more code than you have? Yeah.
It works.
No, good. Yeah, I'm sure there's ways you could probably clean this up. All right, so insertion sort. Questions on the insertion sort. So one of the things with these algorithms, even though these are relatively simple in terms of algorithms, they're not necessarily simple in terms of comprehension, right? So yeah, I walked through it, but you saw it's kind of hard even to explain walking through it everything it's doing. Some of the sorts we're going to get into now are vastly more complicated than this. So the one we're going to talk about next is called quicksort. And quicksort was invented basically because this stuff's too slow. When you get to millions and billions of items, it just doesn't cut it anymore. So they came up with, you know, they experimented, whoever, I don't know exactly who invented it, but some dude probably was hanging out and was like, oh, we need a faster sort because my machine that holds 64 bits of memory can't sort all this stuff effectively anymore, or whatever. So quicksort, one of the things about it is it's not very intuitive how it works. It's actually kind of almost like a puzzle how they implemented it, and I know I would have never thought of it myself, but at all. Even though I was studying sorting, I'm not good at this kind of stuff, right? Like this is where I'm like, meh, I don't really care about the algorithms, and you know, they're nice to know about and all that stuff, but frankly, I can't think creatively like this. I'd go with the selection sort and be like, that's good, I guess. Well, the quick sort is done by default in JavaScript, so most. Yes.
I want to know how it works.
Yeah. Give me a package that's efficient, and we're good. So, one of the things I've stressed a lot through this class too is writing clean code that's easy to understand. Well, another thing with these algorithms is they get more and more sophisticated, like the quicksort. There's no real way to write them in a clean way that's easy to intuitively understand. They're complicated. Just their nature is complicated, right? Because they're very sophisticated in how they solve these problems. So we're gonna end up viewing code that's really kind of dense and hard to understand. Now, the reason why quicksort's so much more effective is its best and its average times are significantly better than insertion and selection sort. So there comes a point where what you're doing is so much better that it's worth that extra complexity, right? So we always strive for the most maintainable and readable code, but sometimes something's just so much better that you're like, you know what, we gotta deal with it, right? For whatever we're trying to do, this is so much better. So quicksort's funny because the worst case scenario is just as bad as the selection and insertion sort. And generally speaking, you compare that worst case scenario and say, oh, well, if the worst case isn't any better, then, you know, is it really better? Well, with quicksort, the answer is yes, because almost never does it actually run into the worst case scenario. There's very specific cases that cause that. And depending on how sophisticated your implementation is, it's almost always significantly better in practice. So the best case scenario is this omega n log n time, which is a complicated time, right? To compare it to n. It's not linear. It's linear plus a little bit of logarithmic flavor at the end. So it's going to take a little bit longer for every item you add to the array, but only marginally so. So you could think of it like if I have 10,000 items, it's going to take me 10,000 loops plus just a little bit. And if I have 100,000 items, it's going to take me 100,000 loops plus just a little bit more than the 10,000. And so what happens is when you get to a significantly larger sample size that you're trying to sort through, this best case scenario and this average case scenario are so much better. So much better, it's outrageous that it's just worth dealing with it. And so that's why when, you know, in JavaScript, below 10 elements we have the insertion sort because it's real simple and it works fine. And below 10 elements you're probably not going to get the speed advantage of quicksort, and quicksort's just complicated. But above 10 elements we start to see this serious difference in how well it performs. It's just outrageous how much better it is. So it's worth it, right? And we get to hundreds of millions and billions of items, it's significantly better, so you almost always do it. So let's see if this All right, I'm gonna show you the implementation first. So this is a cool website because it kind of explains things and then it shows you the sort visually. All right, so let's look at it. It's gonna be kind of hard to follow what's going on. Okay, so it didn't look too crazy because it's kind of hard to follow, right? And this is a small sample size, so it's hard to see really the benefits. But if we did this with a significant sample size, you definitely see it. But what happens in this sort, I'll open it up again. What happens in the sort is it finds something called a pivot. And you could effectively think of this as a random number that you're going to pick out of the array. But your pivot is like somewhere near the middle of the array. Ideally, you pick the number that's supposed to land smack dab in the middle of the array, right? And what it does is it takes that pivot and it starts breaking down the left side and the right side of the pivot into subarrays. So you have 9 items. You pick item 5. The items before that and the items after that are subarrays. Okay? So what you can do is pick pivots from those subarrays, and then you can break down those subarrays into more subarrays. And eventually you get down to this point where you have everything split into individual arrays of one element, which are by default sorted, correct? And what happens is you go up from the pivots and you say, well, now I have this sorted one element compared to this sorted one element. How do they compare? And then you can swap them if you need to, and those are sorted. And then you go to the next pivot, the next subarray that was generated from its parent pivot. You sort those and you sort them in little chunks. And then you come up from that pivot and you start sorting those chunks. And so what happens is, as you come up from these pivots, right, so we end up with just isolated single element arrays, effectively. As you come up from these pivots, the arrays you're sorting are more effectively sorted already. These little pieces of sorts, right? And you can easily sort those into place, or just kind of drop them into place. And so, in practice, it ends up being far more effective. It's hard to follow exactly what's going on here, because it's just a wild kind of sort. Let's see if I can make it faster. But that's what they're doing, and you can actually see this code. They find this pivot, they break into subarrays, they break down those subarrays even further with their own pivots, and then they work their way back up with the sorted subarrays till eventually they get to this fully sorted array. The process of breaking down those subarrays is called partitioning. So they find a pivot, they partition subarrays, they find a pivot, they partition subarrays, all the way down until you go back up through the chain. So this is not a trivial sort to implement at all, right? It's pretty confusing how it works, and just explaining it to you pretty much doesn't tell you how it works, right? You kind of, for me, I had to see a code implementation and kind of walk through with a debugger before I really understood it. And, you know, it's been so long since I've even looked at the implementation of sort, I honestly don't remember exactly how to do it off the top of my head. Because, why would you, right? But, what's important to note is why we use these kinds of sorts, why people develop these kinds of sorts, when to use them, like Matt was asking, when should we use this sort? Should we always use quicksort if it's pretty much guaranteed to be that much better? And the answer is no. There's certain scenarios where maybe you want just a really simple sort because you have a few items, or maybe you need something that's more effective in some way. So maybe a merge sort's better, but it takes up more space or something than a quick sort. And so quick sort's more space effective, right? So there's questions like that you have to ask, and it really depends on what you're trying to do. And this is where algorithms are, you know, very much dependent on the problem and stuff like that, right? And that's why there's whole degrees, computer science degrees, built around these problems. Finding more effective algorithms, more efficient algorithms in space and time complexity, finding when to use them and stuff like that, right? So your JavaScript .sort, when you have an array and you do .sort, if you have more than 10 items, it's going to call a quick sort implementation. If you have less than that, it's going to be an insertion sort. And there's actually, oh man, their link broke. So why don't we look at our little implementation that they gave us, which is in activity 5. Come on. Alright. Alright, so this dot sort will effectively do it for you. So what would the implementation actually look like? Well, we have an unsorted array. What we have to do first is find a pivot, right? So we got to find our place in an array where we're going to be splitting the array into subarrays, a left and a right. From there, what we have to do is determine if something is less than that pivot number. Okay, so say our pivot number is 5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 in an array, and they're all unsorted, and our pivot number happens to be 5 because we're very lucky. We can look through that array. If our number is less than our pivot, we put it in our left array, our left subarray. If it's greater than our pivot, we put it in a right subarray. And then what happens is, when we're done, we're going to run this algorithm again recursively with the left and the right, which is going to break them down even further. And then at the very end, we can just add them all back together, right? So we'll come back in here and we'll have, 3, 2, 1, 4 or something. In this array, we'll pick pivot, say it's 2. We'll say, hey, is 1 less than or equal to 2? Put it in the left. Is 2 less than or equal to 2? Put it in the left. 3, put it in the right. And you break down until you've got all of these subarrays. So why don't we walk through this one? It's going to be a little bit more complicated to walk through, but this one's really hard to visualize. Okay, so we have an array of come on, array.length. My debugger does not like whatever's going on right now. Come on, this is like frozen. Well, we have a huge array, 400,000. It probably doesn't like that. Okay, so we have this huge array, and we have a pivot that it picks randomly, which is going to be 100,860, looks like. Then we loop through everything. Hey, this element is this greater than or less than the pivot? I don't know. And then it looks like it was greater than the pivot. So this 308,000 is greater than the pivot. So it's going to be pushed into the right. The next element, 278,000, pushed into the right. Let's see if we can get a left one. This is a big array, so I'll just set a breakpoint. There we go, we got a left one. 56,449 is less than that 100,860, so it goes in the left array. After all is said and done, what we're going to have is a giant left array, a giant right array, which you can see right here. 101,000 in the left array, 298,000 in the right array. And then if I hit F5, and I start going even further down, you'll notice this is that left array. It's now been broken down into 2 arrays itself. And then again, if I go through it, it's going to be that left array, and then that left array, and then that left array, and then that left array, and so on and so forth until we start to get to really small arrays. Eventually, these are going to be arrays of 1. So the right has 0 in this case. And there we go. We have arrays of 1. And now we start going back up. And we start having sorted subarrays to an extent, right? And slowly it starts going all the way through these chains until all of them have been sorted, one element at a time. And it does not like this implementation. Quick sort. Quick sort. Come on. So one of the problems with this implementation is it creates a subarray every time it loops through, right? And so what happens is, while this is probably pretty time efficient, even so, because it is a quicksort implementation, it's very space inefficient because we have tons of arrays, just arrays on arrays on arrays everywhere. And who knows when they're going to go out of memory or whatever. So that's all well and good, but there's a better example that's in place. It's called in place. So this one is even more complicated to try and follow because we're not building subarrays necessarily. We're swapping items in the array. So this gets complicated. This is dense, right? We have this quicksort function. What it's going to do is it's going to partition the items based off some pivot, and then it's going to go ahead and resort based off of the indices that it determines that fit the partition. So in this partition, it picks a pivot. It could be some random pivot. The first iteration is going to be probably something random, right? Well, it could be something random. It should be something random. In this case, we're just passing in 0, it looks like. But it's going to be some random pivot, and then everything before that pivot is going to be the left array, and everything after the pivot is going to be the right array. And we have to take, we have to basically loop through this and increment the I, so increment the left, decrement the right, until we've reached the pivot effectively, and then we can start swapping item. Honestly, this is really complicated. It takes a while to like understand exactly what's going on, but this one is way more efficient than the last implementation in terms of space. Okay, so we start with an array of 400 items. Our left is just 0, and our right is 399, right? So whatever's at index 0, 296 is what we're going to start with, which is actually a pretty fairly well-centered pivot. So our pivot, 296, we start from 0 and 399. Those are our lefts and our rights. Basically, we're going to jump through this entire thing, add 1 to I, remove 1 from J. So while the item at I of 0 is less than the pivot, and they're the same, so it won't be, we would increment I, and we'd keep doing that. While the item at J is greater than the pivot, which it is, we can decrement J, so 398. If I is less than J, which it is, so again, I is 0 and J is 398, so 0 is 296, and 398 all the way down here is 239. It's going to swap those, which is just a simple swap, nothing crazy, and go through it again. And it keeps going through this and kind of like doing this in-place swap. And then what we get is a J. J comes out, I believe, is the next pivot. It's going to act as the next right. And then after everything after that J is going to act as the, or this is going to be the left and the right, right? So it's going to basically go by indexes, and it's going to slowly filter through the indices there and swap them in place with just keeping track of the indices. So what it's trying to find is at what points can we determine this pivot, and what can we sort inside of that pivot quickly and easily. And then it gives you a new pivot to partition your next subarray, right? So walking through this code can be quite helpful. But again, this is a very complex sort that you're never going to have to implement yourself. If you do, it might be in an interview because someone is a sadist and has decided that interviewees should implement a quicksort. But as long as you get the gist of the time complexity and the space complexity, you're usually okay. And knowing about a quicksort and why it's useful is better than having to implement it. That would be a crappy interview question, but it could potentially happen. You know, I've heard of worse. So that is the quicksort. It is a beast. Alright. So, you can look through that algorithm because you do have the source, the solved solution. The next activity is to pseudocode the quick sort, which we could do it or we could not do it. We could say we did it. It's kind of up to you guys. If you want to pseudocode the quick sort, by all means you can. If you want to try to implement a quick sort based off of the requirements of a quick sort, you can go ahead and try. It's tough. It would take a long time. So I'm going to leave this up to you. If you want to do the pseudocode for the quick sort and keep working through it with me, just go ahead and stay here. Otherwise, go work on your group projects. I'll let you know that today's class was supposed to take the entire time going over these sorts. And so I did you all a favor and got rid of that. So go ahead and go work on your projects if you don't want to know anything more about sorts.
Get out of here. I don't want to see that.
I implemented it the other day. I just kind of tested it. I was trying to test it on Monday, but I kept getting this error and I didn't know why. And then I realized I was making GET requests to post gravel. It wasn't working. I was trying to set it to use data while I didn't do it at the same time. But it worked.
It's like
one page instead. Yeah, and then I'm gonna go out to the user file.
yeah. Oh.
Are there any streamers? Andy, you streaming today? Well, I'm gonna stop streaming then.